This is video 5 for the light unit. So for this one, let's begin by talking about dispersion. When light enters a diamond, unless that light hits the diamond exactly perpendicular to the surface, it's going to bend. And the reason why it bends is because light bends towards the slow. So when the light hits the diamond at an angle, the side of the light that hits the diamond first slows down while the rest of the light is still traveling fast, and that causes the light to bend towards the slow. So what I have here is a prism or a piece of glass, and you can see how when this light beam entered this slab of glass right here, use a different color, make it a little easier, we see that it bends, and we see that it's bending toward the slow. Now when the light re-enters the air, it speeds up. So we can see how it kind of bends away from the fast, if you will. Another thing to notice, the light entering is parallel to the light exiting. So the speed of light is going to depend on the frequency. So the different colors are going to bend different amounts. And we call this effect dispersion. So when we separate white light into its different colors, we say it's dispersed. So just to give you some examples of this, we can go back to the index of refraction, which, remember, it was the speed of light divided by the speed of light inside that material. So if I have different colors, so let's say I have red, yellow, and blue, the index of refraction in glass, and the index of refraction in water. For red, it's 1.5. So notice then that as we go from red to blue, the index of refraction increases. So remember that when we go from red towards blue, the frequency increases. So for higher frequency waves, they have a higher index of refraction, which means that they bend more. So when we have white light entering this prism, higher frequency lights are going to bend more than lower frequency lights. And this causes the white light to be separated into its different colors or its different parts. And again, this is a phenomenon that we call dispersion. Now we've been talking about bending and Snell's law and things like that. So all of that is called refraction. Now for water, since it has an index of refraction of 1.33, light leaving the surface is bent, and that gives rise to many illusions. So one of the strangest of these is the swimming pool illusion. When observed from an angle, the pool appears to be much shallower than it really is. Light from an object on the bottom of the pool is bent as it emerges from the surface, and it bends towards the water. And this makes it look as if the object on the bottom is not as deep as it truly is. So that's something to think about. Next time you're at a swimming pool, look at the water from an angle, look at the deep end, and then look at the shallow end, kind of compare them. And it should look shallower than it actually is. Some other things we can do, if you ever go fishing, and if you see a fish at an angle, realize that it's closer to you than you think it is. Because as light from the fish exits the water, it bends towards the fast. So you think the fish is a little higher and a little farther away than where it actually is. And then there's this classic example where we have an object in water, we're viewing it at an angle. It appears to be broken because of the index of refraction. Lenses take advantage of bending light. Um, and they truly are a wonderful invention. So one thing that lenses can do is that they can focus light onto one spot. So we can have a curved surface. At the edges, the light bends more than light entering at the direct center. So here's an example of a lens. We have parallel light beams, or light rays, coming into the lens, and they are bending and being redirected to a certain point, a focal point. We have focal length, we have a bunch of different things, and there's some math formulas that you can find to calculate the focal length based off of the curvature of the lens. So one thing we could potentially do is we can use this lens to focus sunlight to start a fire. You know, it's also the reason, so you have a lens, a natural lens in your eye, and your pupil for your eye can be larger than a pinhole. So what the lens does is, since your pupil is larger than a pinhole, remember that if you have a really large pinhole, the image gets blurry. So what happens is that you have a lens that takes the blurriness out of that image. So if I had a pinhole camera with a very, very wide pinhole in it, if I were to use one of these lenses, I can take the blurriness out of the image. Now, we have a couple applications for lenses: telescopes and microscopes. So if the object is really far away, like a star system, we say we need a telescope. If the object is really, really close and small that we need to see, we say it's a microscope. So here are a couple examples of some telescopes and microscopes. So let's go back to the pinhole camera example, or we're talking about the pinhole camera. So if the object is close to the pinhole, the image will be larger than the object itself. That's why, or that is what a microscope does. So to see this image, the screen lens, or the second lens I should say, is called the ocular, and it's placed in front of the eye. For a telescope, an image is made of a distant object. So we have to use lenses to kind of focus in some of that light from a very, very distant object. All right, so some famous telescopes that we can talk about are the Keck telescopes and the Hubble telescope. So in astronomy, the problem is, not only magnification, but also collecting enough light to see a dim, distant object. So most astronomers, when they're talking about their telescopes, they talk in terms of diameters. So the most powerful telescope in the world is the 10-meter telescope at the Keck Observatory. And here's a picture of those telescopes. They are massive. They have problems though. So one of the problems though, even though these are located on a mountaintop, so even though they're on a mountaintop, their images are still blurred from the turbulence in the air. And this is going to be true for any ground-based telescopes. They suffer from the fact that the air and air pockets form tiny little lenses that continually change the focus. And part of that also is because air will refract light. So, to kind of rectify this, we went to outer space. Get rid of the air. So that's where the Hubble telescope comes in. Now, you'll notice it only has a diameter of 2.4 meters, so it's significantly smaller than the Keck telescopes. However, because it's above the atmospheric distortions, it can focus much better, and it can see things that are much, much smaller than, in their apparent size, than the ground-based telescopes can. So the distortion from the air pockets, the distortion from the air pockets, it does lead to one pleasant feature. That's what makes stars twinkle. So when you look at a star at night, you may notice that it kind of looks something like this. It kind of twinkles a little bit. I'm drawing it a little exaggerated, but that is actually a result of distortion from our atmosphere. So if you were to go to outer space and look at stars in outer space, they would not twinkle. Kind of sad, maybe. All right. I think we're going to go ahead and stop the video here, and then we'll have one more video to finish up this unit.